All right, let's dive right in today. We're taking a deep dive into the world of electrical circuits.
A fascinating world it is.
Yeah, and you sent over some pretty cool stuff for this. I mean, course notes, study guides, some diagrams I barely understood.
Well, hopefully we can break it down so everyone listening can, well, understand. This stuff isn't just for like electrical engineers and electricians. It's for anyone who wants to understand how, technology works.
Exactly. So let's start with, I guess, like, what are series and parallel circuits? I feel like I've heard those terms, but could never quite.
Yeah. So think of it this way. Imagine electricity like a flow of, let's say, electrons moving through like a pipe, right?
Okay, I'm with you.
In a series circuit, all the components are connected in a single line, one after the other. So there's only like one path for the current to flow through.
So like a single lane road where all the cars are stuck in the same traffic.
Exactly. And that leads to some interesting consequences for how like current, voltage, and resistance behave within the circuit.
Okay, so resistance is like how much the circuit kind of pushes back against that flow of electricity, right?
Precisely. It's like friction in our pipe analogy, right? So in a series circuit, the total resistance is simply the sum of all the individual resistances. Like if you add more components, the resistance goes up and less current can flow. There's actually a formula for this. Total resistance, or RT, equals the sum of all the individual resistances. So R1 plus R2 and so on.
Okay, so more components in series means more resistance, like adding more roadblocks on our single lane road.
Yeah.
Makes sense. But what about voltage? What is that in a series circuit?
So voltage it's the electric potential difference or the push that makes those electrons flow. Think of it as the pressure in our water pipe analogy.
Okay, the pressure. Got it.
So in a series circuit, the total voltage is divided up amongst all the components.
Oh, interesting. So if one component needs like a lot of voltage to operate, the others get less?
That's a trade-off, yeah. It's like sharing, I don't know, a pizza. If someone takes a huge slice, there's less for everyone else.
Makes sense.
And then there's current. Current's the rate of flow of charge.
Okay. So current is like how many electrons are zooming through the circuit at a given time? How's that affected in a series setup?
In a series circuit, well, the current's the same at every point along the circuit.
So it's like that single lane road, everyone's stuck going at the same speed?
Exactly.
So if we wanted to like actually measure these things in a real circuit, how would we even do that?
Well, we have tools for that.
Okay, good.
So an ammeter measures current, and you got to place it directly in the path of the flow.
Got it. So it's got to be like in line with the traffic to count the cars.
Precisely.
What about voltage?
To measure voltage, we use a voltmeter. And this one is placed across a component not in line with the current.
So the voltmeter is like measuring the pressure drop across that particular part of the circuit.
You got it, exactly.
Okay.
And lastly, we have the ohmmeter to measure resistance.
Makes sense.
That's useful for checking the resistance of like individual components before you connect them.
All right. So we've got our rules of the road for series circuits, and we know how to measure things. Now, what about parallel circuits? Those are like the multi-lane highway versions.
Precisely. In a parallel circuit, components are connected on separate branches. So this means the current has multiple paths it can take.
Ah, so like a highway with multiple lanes. Rush hour traffic's going to flow a little better here. How do the rules change in a parallel circuit?
Well, let's start with voltage. Unlike in a series circuit, the voltage is the same across each branch of a parallel circuit.
Interesting. So each branch gets the full push, regardless of how many components are on it.
Exactly. It's like each lane on the highway has the same speed limit, no matter how many cars are on it.
Oh, okay.
Now, current in a parallel circuit, that splits up at the junctions where the branches, divide.
Okay, so more lanes, more options for the current to flow through. Does that mean the total current is higher in a parallel circuit?
Yes, the total current in a parallel circuit is the sum of the currents in each branch. And finally, resistance.
Okay.
In a parallel circuit, adding more branches actually decreases the overall resistance.
Wait, so adding more components makes it easier for current to flow. That seems a little counterintuitive.
It does, but think of it like adding more lanes to our highway, right? More lanes, less congestion, even if there are more cars on the road overall. It's a bit more complex to calculate, but the takeaway is more branches, lower resistance, more current can flow.
Okay, this is blowing my mind a little bit. So we got these two very different ways of setting up circuits, each with its own set of rules. But why does this even matter in the real world? Where do we use series and parallel circuits?
Well, let's start with series circuits. Think about something simple, like a flashlight.
Okay, a flashlight.
You've got a battery, a switch, and a bulb, all connected in a single line.
So it's a series circuit because there's only one path for the current to flow to light up the bulb.
You got it. Now, series circuits are great for, like, simple applications like this, but they have limitations.
Like what?
For example, if one component fails, the entire circuit breaks. Imagine if all the lights in your house were wired in series.
Uh-oh. Let me guess. One bulb burns out and the whole house goes dark.
Exactly. That's why parallel circuits are so important for more complex systems. Like, think about the wiring in your house.
Okay, yeah.
Each light, each appliance, they're all connected on their own separate branch.
Right.
That's a parallel circuit.
Okay. So that's why I can turn off like a lamp without shutting down the entire house's electricity.
Exactly. It's more than just convenience, too. In a parallel circuit, each branch receives the full voltage, ensuring that devices operate at, like, their intended power levels.
Makes sense. What about something more complex, like my smartphone?
Yeah.
It has so many different like functions going on at once. It can't all be simple series or parallel circuits, right?
Most real-world devices, they use a combination of series and parallel circuits. Oh, okay.
They're all working together, like a team.
So it's like a city with different districts, each, like, specialized for certain tasks.
Yeah.
But they're all connected by the same, like, power grid.
Exactly. Think of it this way. Your smartphone has various modules, each dedicated to a specific function,
Okay.
like the display, the processor, the camera, and so on.
And within those modules, you'd find both, like, series A and D parallel arrangements, depending on what needs to be achieved.
Precisely.
So, for instance, like the camera module.
Yeah.
It might use a series circuit to control the flash, ensuring that the current flows through all the necessary components, but in the right sequence.
Right.
But the touch screen, with all its, like, individual pixels, might use parallel circuits.
Yeah.
So each pixel can be controlled independently.
You got it. It's this intricate kind of dance of series and parallel configurations that allows your phone to do so many things at once. Huh. This is making me look at my phone in a whole new light, literally.
Yeah.
So we've gone from like simple flashlights to smartphones. It's incredible how far our understanding of circuits has come.
Yeah.
But like, who are the people who first started unraveling these like electrical mysteries?
Well, there were many brilliant minds, but one name that always stands out is Alessandro Volta.
Volta, as in like the vol each.
Exactly. In the late 1700s, Volta invented the voltaic pile. It was the first electric battery.
Wow, the very first battery. That must have been a game changer.
It was. It allowed scientists to experiment with steady currents for the first time.
And then what?
Well, in the early 1800s, there was a German physicist named Georg Ohm. He did a lot of experiments to understand the relationship between voltage, current, and resistance.
And that's how we got Ohm's law, right?
Yes.
That equation seems pretty fundamental to like everything we've been talking about.
Absolutely. Ohm's law states that the current flowing through a conductor is directly proportional to the voltage across it. It's one of the cornerstones of electrical theory.
So Volta gave us the battery. Ohm gave us the law that governs how circuits behave.
Yeah.
Were there any other big players in this like electrical revolution?
Well, you can't talk about electricity without mentioning André-Marie Ampère.
Okay.
He was a French physicist who was really, really into the connection between electricity and magnetism.
Ampere, as in the ampere, the unit of current.
That's right. Ampère, he figured out that a flowing current creates a magnetic field.
Oh, wow.
And that a changing magnetic field can induce a current. This is like the basis for how electric motors and generators work.
So we have Volta's battery to provide the push, Ohm's law to describe the flow, and Ampere's discoveries to link it all to magnetism.
It's remarkable.
It is.
These fundamental discoveries made, centuries ago, they underpin the entire electrical world we live in today. From, the tiniest microchip to the power grid that spans continents.
It makes you realize that even the most complex technology is built upon like these seemingly simple concepts.
Yeah.
And it all started with a spark of curiosity. Okay, so, wow, we covered a lot of ground in this deep dive.
We did.
We started with the very basics, like defining series and parallel circuits.
Yeah.
And that single lane road versus the multi-lane highway analogy. And that really helped me like visualize it.
Analogies, they're great tools for understanding these concepts.
Yeah.
So in a series circuit, the current faces the total resistance of all the components,
Right.
while the voltage, that gets divided
Yeah.
in a
Yeah.
parallel circuit.
Yeah.
Well, each branch gets the full voltage, and the current, well, it has multiple paths to flow.
We even learned like how to measure these electrical quantities using, ammeters, voltmeters, ohmmeters, like little detectives of the electrical world.
Exactly.
And we've seen how like these circuits are literally all around us,
Huh?
from simple series circuits in a flashlight
Hmm.
to the much more intricate combinations of series and parallel circuits that power like our smartphones.
It's amazing to think that the same fundamental principles that govern a simple circuit are at play in, these incredibly complex devices.
It is.
It really highlights the elegance and power of like basic physics.
It does. And this understanding opens up a whole new way of like looking at the technology we use every day.
Yeah.
Next time I like flip a light switch or charge my phone, I'll have a much deeper appreciation for the intricate dance of electrons happening behind the scenes.
You will. It's quite fascinating.
It is.
Yeah.
This has been a truly electrifying deep dive. Thank you so much for taking us on this journey through the world of circuits.
It's been my pleasure.
And to our listener, keep that spark of curiosity burning.
There's a whole universe of knowledge waiting to be explored out there.
Absolutely.